In this video, I'm going to start talking about the metric tensor. And so the way to sort of, I guess, intuitively interpret the metric tensor is that the metric tensor induces a metric onto your space, which gives length a meaning. So it gives a length to a change in coordinates. So if you're in a space and you change coordinates, uh, that's kind of meaningless until you have a metric, and that's what tells you the length of that change in coordinates. And so we have, for instance, the Euclidean metric, which is well, it's essentially the Pythagorean theorem. And so that's what I have over here. So this actually shows two different types of metric. And so there is the first kind, which is shown in red, blue, and yellow, which is called the taxicab. The taxicab, or sometimes the Manhattan metric. And so that's the metric that's essentially, how far you had to drive to get from, so this point here over to this point. And so if you take the red course, the blue course, or the yellow course, you're going to drive the same number of miles or blocks or the same distance to get from point A to point B, where the green is the Euclidean metric, and you could maybe even call it sort of the metric as the crow flies. So you maybe you've heard that expression that of something is a certain distance as the crow flies, and so that is just the straight line from one point to the other, and so that tells you exactly how far one thing is from the other in the Euclidean sense. So just a straight line, where you can see the other metrics, as I said, would be how far you'd have to go if you drove. And so I don't want to get too much into functional analysis, but the taxicab metric is the summation of I equals 1 to n of the absolute value of p minus qi, like that. And so that's just, this, if this is your P1 and your Q1 here, that's just the distance from here, then this is your P2, P1, and so that distance, so you're just adding each of those distances up, where in Euclidean, so I'll write that over here, that's if we have the summation I equals 1 to n of pi minus qi squared, and then that whole thing square root. And so you can see how if you call this point 0, 0, and then this point is your p, that you would just be, because you're subtracting 0 from it, you would be essentially just taking from here to here, and then from there all the way up to there. And so it would just be the p1 squared plus p2 squared, and then the square root of all of that, which is sort of the same thing as your c equals a squared plus b squared square root. But anyway, I don't want to get too far down that rabbit hole. The idea is that the metric tensor induces this metric, which gives length a meaning. And so that is sort of what the metric tensor is doing. So one of the things the metric tensor can be used for is what's called a bilinear mapping. And so a linear mapping is when we have to bring in that idea of the dual vector. So we have our vector and then our dual vector, which is oftentimes written like that, and that brings us to some scalar. And so you can think of the dual vector as kind of like a function. So maybe you could even write it like this, and then we have this space here, and this is sort of what the input of the function is, which would be some vector, and that brings it to a scalar, where the metric is a bilinear mapping. And so what we actually have, so the metric, which is usually written as G like this, you could think of as, and I'll put the indices here, as a function that looks like this, and then we put a comma here because there are two spaces where you can put things, and those things that you would put in there would be vectors. So you would have G, I, J, and then you would have a vector here and then some other vector, and so the dot product brings that to a scalar. And so the metric tensor can act like a function. So it can act like a function that takes two vectors as input and maps it onto a scalar. Then I put this here, which is from Wikipedia, and this is just showing sort of how the bilinearity works. And so the first one is showing that if you were adding vectors in your first input, then you end up with something that looks like this. So your function with the first term in the first input here, plus your function with the second term in the second input there. Then so it's the opposite if you have the two vectors being added in the second input, then it goes into the second input like that. And the same if you're scaling it. So if you scale just the first input, then you just scale the whole function once like that. And if you scale the second input, then you just scale the full function like that once. Whereas if you, so this is using B, but if we're using our G, so if you did something like, if you had something like this, like our lambda V and then lambda W, this would actually be 2 lambda G, I, J, V, W. And so that, so each of these, if you factor it out, goes in front of it once. And so if you have it in front of both of them, then you would actually end up with 2. And so you can't go like this, like G, I, J, V, W. You can't go from this to the G, I, J, and then lambda V, lambda W. It doesn't work that way. Oops, kind of got pushed down there. So it doesn't work this way. You can't do it that way. So anyway, that is kind of a broad overview of what the metric tensor is. Now, if we want to look at some of the things we can do with the metric tensor, so if we have a two-dimensional Euclidean space in Cartesian coordinates with orthonormal basis, and so what that means is that, well, 2 dimensions, I think you can probably guess what that is. That's just if we have like an x and y coordinate like this. Euclidean space means that it is flat. We're not in, say, like Minkowski space or anything like that. Cartesian coordinates just means that we're using this. We're not using polar coordinates, which would be more like something like that, where we have the r, and then the theta, which so we might be theta like that. So we're not doing that. So it's in a Euclidean space with Cartesian coordinates, an orthonormal basis, which just means that these are right angles from each other. And so we end up getting a metric that looks like this if we put it into the matrix form. So we're Gij. So the first element of it is just the basis 1 dot basis 1. And so this goes to our bilinearity idea. And so that's the idea that if we have G, I, J like this, and so we could maybe have like E, I dot E, E, J like that. And then if we are acting on, say, some vector V and some vector W, the EI only affects the V and the EJ only affects the W. And so that's that bilinearity. And that's why we have to have the two bases in each entry in our matrix here. But since they're orthonormal, if we have E1.E1, that just gives us 1. If we have E2.E2, that also just gives us 1. And E1.E2 or E2.E1 will both give us 0. And so that this metric can also be thought of as the Kronecker delta, which the Kronecker delta is just of this just means that it equals 1 if I equals j and equals 0 if I does not equal j. And so you may have run into the Kronecker delta before. And so if we have the metric in a Euclidean space and Cartesian coordinates with orthonormal bases, then the metric is just the Kronecker delta. And so if we do the dot product using this, we just end up with this. So our V dot W is just what we would expect from a dot product, which is just V1 times W1. So the components of V and 1 of V1 and W1 and the component plus the components of V2, W2. So that would be like if we had our V1, V2 dot W1, W2 vectors like this. And so that is that will be a scalar. So it's just the regular dot product as you probably run into it in linear algebra. And so if we let V, our V vector here, be equal to CD, so CD here, and then our W be equal to AB, and then we do the dot product. So we have this right here. So I put this as a row vector and this is a column vector. That's sort of the proper way of doing the dot product. I mean, in sort of the, I guess, elementary sense, it works like this too, but the proper way is just putting it as a row vector, which actually makes it a covector, but I'm not going to get too much into that. But then the idea is we just act this matrix on our first vector here, which is our vector W. And so that's just 1 times A plus 0 times B. So that's our first entry here. Then we have 0 times A plus 1 times B, so that's our second entry here. And then we just do C times the top entry plus D times the bottom entry, so that ends up with AC plus BD, which once again, that is just our sort of standard dot product there. And then so if we have V equal W, so that C equals A and D equals B, that's just V dot V here. So it's just A. Well, and here I actually put cosine, so I'm actually kind of getting ahead of ourselves. So cosine goes in those two off diagonal, because if we have cosine of 90 degrees, which is orthonormal, they will just equal 0. And so those will be 0 if we have orthonormal bases. But if they're not orthonormal, then we actually end up with this. So we will have our A plus B cosine theta, which up here, if theta is 90, that just makes it 0. But here I put it more explicitly with the cosine. So A plus B cosine theta. So it'll be A times the top entry here, and then B times this bottom entry here. So that gives us A squared plus AB cosine theta plus AB cosine theta plus B squared. So that gives us this right here, which gives us this. If we combine the AB cosine theta and BA cosine theta, we get that. Then right here, once again, if theta equals 90 degrees, so orthogonal, then cosine theta equals 0. And this right here will go to 0. So we get A squared plus B squared. And so that is our Euclidean metric. Remember, I said that was essentially the Pythagorean theorem, which, is C squared equals A squared plus B squared. And so C equals the square root of A squared plus B squared. And so that is our Pythagorean metric. And so we see that if we our Euclidean metric. So we see if we use that Euclidean that metric tensor in a two-dimensional Euclidean space and Cartesian coordinates with orthonormal basis, that we just end up getting our Pythagorean theorem. And so that is why that is the Euclidean metric there. All right, so then if we want to do a two-dimensional Euclidean space and Cartesian coordinates with non-orthogonal basis, so I'm saying that the basis is still normal, which means that each one still equals 1, but they are now no longer orthogonal. And so we're essentially taking this E2 here and sort of bending it down by some angle. And so we now have this angle here, theta, between our E2, which I put as E2 prime, and our E1. So those are our two basis vectors. And so now E2, the E2 prime is going to be equal to, because we now have to put it in terms of the E1 and E2. So our E2 prime is going to be equal to cosine theta times our E1 plus sine theta times our E2, because this is our sine theta times E2 and this is our cosine theta times E1. And so if we take the dot product of that, which is what I'm doing right here, then we substitute in for this E2 our E2 prime, which is this right here, our cosine theta E1 plus sine theta E2, and now we're dotting it with the E1. So with the E1, so E1 times E1 is just 1, then our E1 times E2 is 0, and so we end up with our E1 dot E2 being equal to this, which, as I said, is just cosine times 1 plus sine times 0. So that goes away, and we have our E1 dot E2 just being equal to cosine theta of E1 dot E1. And so now we can go over here. So this is, once again, so I have the E1 dot E1 equal to 1, the E1 dot E2, which is equal to E2 dot E1, that is symmetric, equal to our cosine theta, and our E1 dot E2 equaling 1. And so this right here is where we got cosine in the off diagonal parts of it. And so that's where we get the cosine in the off diagonal because the sign, like I said, went away because it was times 0. And so the E1 dot E2, which is what we have here, and then the symmetric version is right here. That's how we get cosine theta in those off diagonal. And so now if we have two vectors here, v dot w, and we use here our metric tensor to do the dot product, and we have w equal to ab and our v equal to cd here. So the first thing we do is multiply through, so 1 times a plus cosine theta times b, that's our first entry here. Then our cosine theta a plus 1 times b, that's our second entry here. Then we multiply c times the first entry and d times the second entry. And so we end up with ac plus ad cosine theta plus bc cosine theta plus bd. And so it's sort of like our Pythagorean thing, where, because if we say that that v is equal to w, then this cd here just becomes ad, and what we end up getting is this down here. And if we are in orthonormal basis, cosine theta is the cosine of 90 degrees, which just equals 0, and so this part will go away, and we just recapitulate our Pythagorean theorem here. So v dot v equal a squared plus b squared. And so if we have two vectors that are non orthogonal from each other, we can just sort of adjust the basis vectors so that they are pointing along our vectors. So here we have v is equal to some constant c times e1, because we have to go from here to here, and then plus our component times e2, which brings us up to here. Then this one is our component times e1, and then our second component b times e2, which brings us up to here. But if we change the basis here so that our v is just equal to this single component here, d times e2, because there is no e1 part of that vector, and same with this one down here. So we adjust the bases to point along the vectors v and w and take the dot product. And so now we have 0 d here because we have 0 in E1, and then D is just times our E2, so we only have that D component. And then the same here, we have our A and then 0. So we end up with A plus 0 cosine, A cosine theta plus 0. Then we multiply this by that up there and this by that down there, so we end up with this 0 here, so that goes away. Now we have this d times a times cosine theta. That gives us our ad cosine theta, and that is how we actually get, so you may have seen this as a definition of the dot product here, where v dot w is just equal to the magnitude of v times the magnitude of w times the angle between them, and so that is our ad cosine theta. And so that is sort of the other version of the dot product that you may have run into, and we can see how that once again comes from having this metric tensor right here. So that metric tensor is where that cosine sort of comes from in that version of the dot product. So I said this is the other version of the dot product. So the first version that we talked about was where we had our v dot w. So our v dot w, which was equal to our v1 w1 plus v2 w2, and that could go on depending on how many dimensions we are in. And so this other version is v dot w is equal to the magnitude of v times the magnitude of w times the cosine, so of the angle between them. And so we can actually see in that sort of bilinear form here where our v dot w is this a, so this component of v times the E1 dot our component of D times the E2. We pull the components out because this is linear. We have our AD times our E1 dot E2. And so our E1 dot E2, remember, is our E1 dot the cosine theta E1 sine theta E2. And so once again, this goes to 0, and that just gives us our E1 dot E2 equals cosine of theta times our E1 dot E1 here. And so that, once again, is just another way of thinking about it, but in terms of the basis vectors here of our dot product. All right, and so that is sort of the idea of the dot product and how the metric tensor figures into the dot product. If we are in this orthonormal basis, the metric tensor, like I said, is just the Kronecker delta, so it's just this diagonal matrix with one as the elements there. And then if we are non-orthogonal, then we end up with this cosine in the off-diagonal parts of our metric tensor. Once again, still in Euclidean space, though. In future videos, I'll start talking more about the metric tensor in things like Minkowski space and things like that, which will be a little bit different. But for now, we're just trying to get an idea of what this metric tensor is all about. And so the metric tensor can also be used for finding the components of two vectors v and w. So we have our v dot w here. So this is sort of looking at it in that sort of bilinear function form like this. And so we can actually expand that out into this. And so once again, I have that outer product or tensor product version of our EI and our EJ there. And then we are sort of acting that as like a function on our two vectors here, where these are the vector components, the VK and the WL. Then these E's are our basis vectors. And so we have the metric tensor here. So this is still the same thing as having this here. I'm just leaving it implicit. Depending on what source you're going to for learning about this, you will see people leaving that circle multiplication there implicit. Some people will always show it explicitly. So it's just another one of those many things that you have to get used to in math. And so we have this here. So then we pull out the components and then put the bases into here. So the first one will go to here, and then the second one will go to here. And so once again, that's that bilinearity that I was talking about earlier. So now we have the components out here, and we have inside here this first basis and then the second basis. Well, then these two bases just turn into the Kronecker deltas here, because in the first one, only when I equals k is it 1, everywhere else it's 0. In the second one, only when j equals L is it 1, everywhere else it is 0. And so now we have this right here, which gives us the components for V and W. So those are the components there. So I'm putting it more explicitly here now. So this is just doing the same thing, but doing it in this explicit matrix form. So in this first one here, so the first one and the second one are the same thing. The second one, I just put the little symbol here implicitly. So you can look at it explicitly or implicitly. And so we have this here. And so this E tilde 1 will go to this one, and then the second E tilde 1 will go to this one, and so on and so forth. So once again, it's that bilinearity where the first one always goes to the first vector, and the second one always goes to the second vector. And so after carrying that out, we have this down here. So we now have the V1 E1 tilde plus our V2 with E2 times the E1 tilde, because this E1 keeps going to this first vector, plus the V3 times E3 E1 tilde, and so on and so forth. And so these, where it's equal, will end up becoming 1, and then where they are not equal here, they will end up becoming 0. And so that's what I have down here, where I have the first one, so our V vector here, the elements here in green, or the terms rather here in green, are where we have our Kronecker delta. 1 equals 1, 2 equals 2, and then 3 equals 3, and then all these other ones that are still in black, the Kronecker delta elements are just going to be 0. And then the same thing for our W vector here. And so we end up with our V1 times this Kronecker delta element here, which is just 1. So it's just V1 times 1, V2 times 1, V3 times 1. So we end up with these ones here. And so those are the components of our vectors, here, V and W. And so that is sort of how the metric tensor can be used to find the components of our vectors. And so then the last thing I have down here is just the metric tensor for spherical, for polar or spherical, so polar or spherical coordinates here. And we can see that the entries in this matrix are not just, ones and zeros. We have this r squared and this r squared sine squared theta. So this, it's three-dimensional. It's still in Euclidean space, and it's still an orthonormal basis, but now we are in the polar coordinates. And so you can actually see the orthonormal basis right here, where this arrow right here is our ER. This one sort of pointing this way is our E theta, and this one over here is our E phi. And so once again, this gives sort of a meaning to a distance. So when we make a coordinate movement, so if we are just using, so if we're just looking in 2 dimensions, so we have, some vector here, and we sort of move it down this way. So we have this angle here theta, and so the length is r. This metric here gives some meaning of distance, so how far away is this second vector here from the first vector, and so that this metric gives a meaning to distance in polar coordinates. And I just wanted to show this to show that our metric tensor isn't always just going to have nice ones and zeros for its elements, but when we are in polar coordinates, for instance, it will have different elements. And if we're in a different kind of space than Euclidean space, so if we're in Minkowski space, which I'll talk about more in future videos. So the Minkowski metric, which mu and nu, and this is often written as eta, which I can't draw etas, or kind of like that, with mu, nu, we'll have the minus 1, 1, 1, 1, or alternatively, you'll see it as 1, minus 1, minus 1, minus 1 in the diagonals, where all the off diagonals will be 0. So you'll see it in both of these kind of forms like this. And like I said, I'll talk a bit more about these and what's different about the transformations using this metric compared to just the Euclidean metric. But anyway, that's getting a little ahead of ourselves. Like I said, the takeaway from this, so a metric tensor induces a metric which gives a length a meaning. So it gives a length to, it sort of says a change in coordinates in this space will have this length. And so it's also a bilinear mapping. And so it gives a meaning to the dot product or inner product if you want to be a little more sophisticated about it. So yeah, it gives us the dot product, which like I said has these two forms here. And so it gives us the dot product, and it also can let us find the components of V and W. And in the next video, actually, I'm going to talk about how the metric tensor is actually used for those raising and lowering of indices, where, like I said, if we had like a VI, so that we can change the indices with it, so we can have G, then I, J, and then V, J, so that's changing the index on it. Or we could have, say, like a tensor like this, and then we have our G, and we could, if we have like H and K, we could change one of these because it's just sort of a summation index, which I'll get into more in the future, but that will give us our T, I, J, and then our G, J, K, which we sum over the two repeated indices, and that will just give us our T, I, K. But anyway, that is what I'll be talking about in the next video, this sort of index manipulation, and be a little bit more concrete and a little more explicit about what's actually going on with this index notation type stuff. But anyway, I hope you found this video helpful, and I will see you in the next video.